Okay, let's get started on the problems on slide 19. Acetic acid is the principal ingredient in vinegar that provides a sour taste. At equilibrium, a solution contains these concentrations: CH3, CO2H, 0.0787 molar, H3O plus concentration of 0.00118 molar, and the same, so this is also the concentration of CH3 CO2 minus. Okay, first of all, and it asks us to calculate the Ka value. We first need to write the equation. So we do that. We know that this is an acid. We know that CH3CO2H can dissociate with water. Remember, this is liquid, so it won't appear. And as acids are H plus donors, so they donate this to the water molecule, leaving an anion behind, so CH3CO2 minus, and this is aqueous. Oops, I wrote it in the wrong spot here. Aqueous. This is aqueous plus H3O plus, which is aqueous, and plus there. So let's write the Ka expression. Ka is equal to the the concentration of each of my products, CH3CO2 minus, times the concentration of H3O plus. Now, because they have one as molar coefficients, the powers will be 1. If they had more, then it'd be whatever the coefficient would be in front. And then all of this is over the concentration of CH3CO2H. Note that I don't put the concentration of H2O because that's a liquid and it's 1, so it cancels out anyway. Now let's plug in all the numbers we have. These two are the same, so I can write 0.0018 squared divided by the concentration of my acid, which is 0.078. This gives me 1.77 times 10 to the minus 5th value for Ka. Now let's look at problem 2. Problem 2 says the HSO4 minus ion is a weak acid used in some household cleaners, and it tells us what the equation is. I'm not going to write it for lack of space, but you can follow along. What is the acid ionization constant? So what is the Ka value? That's what the acid ionization constant means. For this weak acid, if an equilibrium mixture has the following composition: H3O plus concentration is 0.027 molar, HSO4 minus is equal to 0.29 molar, and SO4 2 minus is 0.13 molar. Well, based on that reaction that we have given, I mean, we could write it, but I'm not going to. You can just follow along. We will write a Ka expression, which is equal to the concentrations of my H3O plus multiplied by the concentration of SO4 2 minus divided by the concentration of HSO4 minus. Now I have all of these values, so all I have to do is take 0.027 times SO4 2 minus, which is 0.13, divided by 0.29. If you do this math, you should get 1.2 times 10 to the minus 2. Now, if we're just looking at these Ka values, it doesn't ask us, but let's talk about it. The Ka value for HSO4 minus and the Ka value for the acid, acetic acid. The HSO4 minus has a larger Ka value. It's 1.2 times 10 to the minus second versus 1.8 times 10 to the minus fifth. That means that HSO4 minus, it's a stronger acid than my acetic acid. The larger the Ka value, the stronger the acid. And the opposite is true. So HSO4 minus is a stronger acid by about 1,000 times stronger than your acetic acid, which means that it will dissociate, it will split up into H3O plus and SO4 2 minus more than the acetic acid will dissociate, which means that its percent ionization, which we did in the previous slide, is higher than that of the acetic acid. It's just a different way to think about in terms of Ka values and strength of acids and strength of bases as well. We'll cover those in the following. So the last two problems of this slide are on bases, so I'm going to erase this and we'll do those. Okay, let's look at the last two problems on slide 19 that deal with bases instead of acids. We have caffeine, which is C8H10N4O2 is a weak base. What is the value of Kb for the caffeine if we have the equilibrium concentrations given? Now let's write, if this is aqueous, let's write the reaction. If it combines with water, then it's a base, so we know it will strip a proton from the water to form an acid. It's conjugate acid. So C8H10N4O2H plus, and this is aqueous, plus OH minus, and that's also aqueous. This is my concentrate, or the reaction, and it's balanced, so I don't need to really worry about that. I can write the Kb the Kb expression by using the concentrations that I know. The concentration of the conjugate acid, C8H10N4O2H plus, times the concentration of OH minus over the concentration of caffeine, N4O2. Now I am told that these concentrations they're given to me, so I am going to just plug them in. This concentration is equal to 5 times 10 to the minus 3 molar, multiplied by OH minus is 2.5 times 10 to the minus 3, divided by the concentration of caffeine, which is 0.05, and that should give you 2.5 times 10 to the minus 4. That's the Kb value for the dissociation of this base, the ionization of this base. Let's look at the next one. So this is problem 3. Let's look at problem 4. What is the equilibrium constant for the ionization of HPO4 2 minus ion? So I have HPO4 2 minus aqueous plus water. Now, because it tells me it's a base, this can act both as an acid and a base, but because it tells me it's a base, I can, there's the reaction. I can write it as a base. So if it's a base, it will strip off a proton from the water to give you H2PO4 PO4 minus, because I took a plus from here, so an H plus minus 2 will leave me just a -1 charge, aqueous, plus, now this becomes OH minus, aqueous. You've got to make sure when you write these that your charges are balanced on both sides. So for example, I have a 2 minus charge on the reactant side, and the product side also has to have the same charge. -1 plus a -1, you have a total of -2. That has to be conserved. Okay, so now that I have the reaction, I can write the Kb value, Kb, just like the equilibrium constants we were writing in chapter 13, but this is specifically for acids and bases, so I called A and B, Ka and Kb. Concentration of H2PO4 minus times the concentration of OH minus over the concentration of HPO4 2 minus. Now I've been given all of these concentrations, so I can go ahead and plug them in. 0.042 times 1.3 times 10 to the minus 6 divided by 0.341. This should give you a value of 1.6 times 10 to the minus 7 for this Kb. Let's compare these two bases. Well, this is, so HPO4 minus has a Kb of 1.6 times 10 to the minus 7th. The caffeine has 2.4 times 10 to the minus 4. This is a larger Kb value than this, which means that caffeine will ionize more, will split apart into these two ions, more than HPO4 will split apart into these ions. So it's a stronger base than HPO4 2 minus because this is a smaller Kb value than that. That is how you can tell the strength of, you can compare two acids and two bases, which one is stronger, which one is weaker. Okay, I am going to erase this one and we're going to move to the next slide and work on the problems on the next slide.